Hello everyone, welcome to another section on data structures and algorithms. This workshop's 9 will be focusing on self-organizing trees. At the completion of this lecture, we expect you should be able to describe a splay tree. You should also be able to create and maintain a splay tree. And lastly, we expect you will be able to differentiate between an AVL tree and a splay tree. I'm convinced you should be able to explain why we need an AVL tree. And you should also be able to explain the node, which node in a tree that has the least consuming time to visit. To recap this, one of the reasons why we need the AVL tree is to reduce the complexity of the operation. And it does that by reducing the height of the tree. I'm not going to answer the second question, it's for you to answer, and I believe you'll be able to answer it. Okay, let's move to the next slide. The self-organizing tree, also known as the splay tree. So a splay tree is a self-organizing binary search tree with the property that recently accessed elements are always quick to access again. So this splay tree principle believes that any element or a node that has been accessed will be easily accessed again. The reason why it is easily accessed again is that the split tree principles will always push the node that has been accessed towards the root node or at the position of the root node. And as you know, whenever we want to search or access a node in a tree, we always start the search from the root node. Hence, if the splay tree always pushes a node that has been accessed towards the root node, then when next we want to access that node, it becomes easier for us to access, or it becomes quicker to access again. So a splay tree is self-adjust after every search, insertion, and deletion operation. So when there is a search or insertion or even deletion operation, the splay tree performs an adjustment that moves the node from one point to another until it gets to the root node. So as the reason we say it has an excellent uh, performance in case of where some data is accessed more frequently than others. And as we have seen in the AVL3, the AVL tree tries to minimize the height of the tree, but the self-organizing tree, which is also known as the splay tree, does not necessarily have to minimize the height of the tree. So the main concern of this operation is to move the accessed node towards the root node. So that's the reason it says the basic assumption is that the most recently visited node is more likely to be visited again. Let's look at insertion operation on using the splay tree. So on the insertion operation, the steps we normally take when we want to perform this operation on a binary search tree is to first locate where to insert the item. And once we have located where we need to insert the item will be inserted and that could be at the new leave node. And let's assume the item we are inserting is else. Then we have to move the root, move it to the root node using a series of rotation. So this series of rotation is known as the splaying. So splaying is the movement of any node to the root node. The movement is achieved through a process known as rotation. The rotation could be done once, it could be done twice. The rotation is also similar to the kind of rotation we performed using the AVL trees. So the split tree always walk from the bottom to the top. The way we want to perform operation, we always start from the bottom towards the top. So, and that involves series of either double rotation until the node, the node which is else in this case reaches either the root of the tree or the child of the root node. So it is reaches the root of the tree or the child of the root node when a single rotation is performed. So let's see the kind of rotations that we have for split tree. So the kind of rotation that we have is one is single rotation, and that single rotation is also known as zig rotation. So this zig rotation is equivalent to the LL and RR rotations in AVL3. And this rotation is only used when the accessed node is the child of the root node. So the effect is that we move the accessed node up to one level. And if we move it up to one level, we'll end up taking the access node to the root node. So another rotation type is the double rotations. The double rotations could be ZigZag rotation, and the ZigZag rotation is the equivalent to the LR and the RL rotations in AVL3. It could also be ZigZig rotation. This ZigZig rotation has no equivalent or equivalence in AVL3. So in this case, what we can do is that the rotation that is performed makes up to two level movements. And that is, you remember in this one, we perform a rotation to make only one level movement. But in this double rotations, the effect is to move the node X, which is the node we are accessing, up to two levels. Now let's have a look at some of the examples. So in this example, it is zig rotation. Remember, we said that zig rotation is equivalent to the LL rotation in AVL3. So if you perform a zig rotation on this tree, we will get this tree at the right hand of this slide. So the operation, as usual, is we have to first of all create a temporal location where we need to move the root node into. And once that is done, we move the target node, which is A in this case, to the top, where the root node, the original root node, comes down to this right-hand side. And we remember the kind of operation we used in the previous slide, where we assume that we have a nail somewhere here, and we are pulling this B down. So So the A will go up and the B will come to this place. So that is the kind of rotation that we have here. So let's look at another example. So this kind of example is the ZigZag rotation. Why is it called the ZigZag rotation? It is a ZigZag rotation because it is equivalent to the left rotation in AVL tree. So if you look at this original tree, we can see that if we perform right rotation here and perform another left rotation here, then we end up taking this B to the position of A. So that is the reason we call it the ZigZag rotation. So at the end of the ZigZag rotations operation, the B position will take the root position, and C retains its position while A moves to the right. So all these sub trees or values could be arranged knowing fully well their original positions. What I mean is this. Now we know that T3 is at the left side of B. So when we move it, we look at this. This is the left side, is at the right side of B. So when we finish moving B, we look at B and find the right side. And the right side is this location. So originally we have C, which has a value T4. So the only place that is vacant for us to place another value is at this left side. So we put T3 here. So the main concern is to ensure that at the end of operation, that this T3, which is at the right side of B, must be at the right side of B. So there's another operation that is ZigZig rotation. In this ZigZig rotation, it has no equivalent to the AVL rotation. And because it has no equivalent, we are not going to follow the AVL rules. Because in the AVL rules, after our operation, we need to reduce the height of the tree. But in this case, we are not concerned with reduction of the height of the tree. So what I mean is this. Ordinarily, we want to rotate this to the root node. We would have performed the operation to a point that A will be at the root node. B will be at the position of A, and A will be at the left-hand side. But in this case, we only made the ZigZag rotation, the ZigZig rotation. And that ZigZig rotation means that we have to move to this place and move to this place. So we are not concerned about the height. We're only concerned about the movement of the target node, moving the target node from its position to the root node. So when we are done with the operation of ZigZig rotation, this is what we're going to have as the outcome. So we can also have ZigZig rotation. The first rotation is to move this to B, and then finally we move this one to this position. So the operation is, if we level this G, level this P and C. First, we have to move the position of the P to G. Then we have to move C to the position of P. So when we're done, we have this in this way. So this another ZigZig rotation. So if you look at the other one, you realize that this rotation is on the right, but in this rotation is going to be on the left. So the operation is going to be similar with the one we did in the previous slide. So the operation or the rotation is going to be, in this case, that we have to move A to B, and from B, move it to C. So it's going to take the position of the root node. Remember, our consign is always to move the target node to the position of the root node. And if it is a double rotation, it can be ZigZag rotation or ZigZag rotation. Now let's perform insertion operation. Now we want to locate where we need to insert this node. And the node is referred to as a C. So first we insert the item C. Then we have to perform split tree operation. So if the item we inserted is in the position of that we need to perform ZigZag or ZigZig operation, then that operation means that the item is not the direct, is not a child or a subtree of the root node. So we have to perform ZigZag operation or ZigZig operation. But in a case where the item that we have inserted is the child of a root node, then we only have to perform single operation, which is Zig operation. So this is kind of algorithm to explain what we had in the previous slide. So our consign here is to perform the split operation on node C. So the first thing is why C is not the root node. We have to check if C is the root node. If C is the root node, then we cannot perform any operation on it. But when C is the child node, we have to perform the Zig rotation. And the Zig rotation will take C to the root node. Or in a case where C is not the child node, we have to find out if we need to perform ZigZag rotation or ZigZag rotation. So in this case, we are talking about the double rotation. For the double rotation, we determine whether the position of C is at the left or at the right side of the root node. So if it is at the left or right, then we need to perform the ZigZag operation. Or if it is either at the right or at the left, then we have to perform the ZigZag operation. Now let's perform or look at the searching operation. So the searching operation is similar to the insert operation that we did in the last one. But in this case, we are looking for the node. So now the two case scenario is we might end up finding the item that we are searching for, or we might end up not finding the item we are searching for. So if it is the case where we are successful to find the item in the location where the item is positioned or located, then we have to perform the display operation on that item. The display operation is moving the item that we have found to the root node. And remember, we can do that either using the Zig operation or the ZigZag operation, or finally the ZigZag operation. So, but in a case where we cannot find the item after our search, then we have to perform the display operation on the last item located to the root node. So there's a question here which says it will be faster to search for the same item after both successful or unsuccessful search operation. So do you agree with this question? Do you agree with this question? You can discuss this during the tutorial section if you agree or disagree. Now we have to look at deleting an item. So for us to delete an item, we have to first of all search for the item and locate the item that we want to delete. And when we locate the item that we want to delete, we can delete the item and so we can perform splay on the deleted item to the root. Okay, then once we have finished performing the splay, yes, once we have completed the splay operation, that is when we have moved the item we want to delete to the root node, we can now perform the operation of deleting the item or removing the item from the tree and replacing the item with another successor or predecessor. So this is one way to achieve that. Another way to achieve that is to remove the item that we want to delete. So when we remove the item that we want to delete, we can now perform the splay operation on the parent of the item that we have deleted. We will see examples to illustrate these things. So, and if unsuccessful search, so that is when the item is not found, then we splay the last item located to the root. So this is an example of splaying value 14. So what we want to do here is that we have to splay this value, which is 14. So what we need to do at this point, you can guess, are we going to perform ZigZig operation or ZigZag operation? That is the first question. So in this case, we are going to perform ZigZag operation because we have to perform an operation that is moving this to the right and moving this to the left. So we have to move this here and move this to the left. Sorry, that is right rotation and left rotation. So that is the reason we have to perform ZigZag operation. So when we perform the first ZigZag operation, we replace 14 with 5, with 15 with 14. And at this point, 14 has not gotten to the root node, so we still need to perform another operation. I want you to think which operation is the next that we need to perform at this point. Is it going to be ZigZag operation or is it going to be ZigZig operation or only Zig operation? So in this case, we need to perform, we are not moving left and right, so we're only moving in one direction. So it's going to be a ZigZig operation. So we are going to replace the value 11 with 14 on performing the ZigZig operation and rearrange these elements. So when we do that, we replace the value 11 with 14 and rearrange these elements. So which other operation do you think we can perform here to move this 14 to the root node? So it's still going to be ZigZig operation. So if we perform ZigZig operation, we move 14 to the root node. So we have 14 at the root node and we adjust other elements to look this way. So at this point, we have completed the operation. One thing I want you to notice is look at this node. Look at the position of 14 and we want to move 14 to the root node. Then on moving 14 to the root node, you realize that these two nodes are at the right hand side of 14, and these three nodes are the left hand side of 14. So once the operation is complete, always ensure that this moves to the left side of 14. So that is the reason we have only 15 and 17 at the right hand, and 12, 11, and 13 move to the left side of 14. So finally, we have reached the end point because 14 has been successfully moved to the root node. Now let's look at the performance of this operation that we have. So based on the operations we have performed, we can realize that no single access operation is guaranteed to be efficient, because the single access operation might not be able to take the identified node to the root node. And we have that the worst case scenario is when the big O notation is of the order of n. So in that case, we have to move through all the nodes that are contained in the binary search tree. So we also believe that over a series of operations, the average tends to become the order of a log n. Sorry, log 2n. That is log n, yeah. So do you really believe that this is the case? One idea I have to give you is that when you are performing this operation, you tend to move almost everything towards to a point where the nodes that have been visited will be taken towards to the root node. So that will reduce the complexity when we want to search for that node again. So, and the answer this question, I will also want you to think about it and see if you can come up with the right answer to this question. So if you cannot, you can just send me an email or discuss that during your tutorial section with Darlene. Now let's perform this activity 9.3. And what we want to do is we want to search for a node 1. After that, we want to delete node 6. And finally, we want to perform the insertion operation that will add node 11. So let's start with the search operation. So the search operation will have to locate node 1. On locating node 1 is the first task we have to do. Then the second task is to move the nodes to the root node. So how are we going to move this node to the root node? We need to perform operations. And what kind of operations are we going to perform? Is it going to be ZigZag operation the first time, or is it going to be ZigZag operation? So in this case, we are not moving left and right. We are only moving in one dimension. So this is not going to be ZigZag. So what we're going to perform is ZigZag operation. So when we perform the ZigZag operation, 1 will take the position of 3, and the 3 will be adjusted this way. So at this point, we still need to perform ZigZag operation, and 1 will take the position of 5, and the 3 will be adjusted again. So at this point, we still need to perform the ZigZag operation, such that 1 will take the position of 7, and the 3 will be restructured to look like this. And lastly, we need to perform another operation. What kind of operation do you think we're going to perform here? Knowing that our interest is to move 1 to the root node, which is at the position 9. So we still need to perform the ZigZag operation. And lastly, we have this structure for our search operation. Now we are going to perform deletion. We want to delete node 6 from this binary search tree, or this tree. So what are we going to do here? What we are going to do here, we can either delete and perform the splay operation, or we perform the splay operation before deleting. So let's take the first one, which is we first delete, then perform splay operation. So if we delete 6, we're going to have the structure looking like this. So our target at this moment is now 7, because 7 is the root node to the element that we deleted, which is 6. Now we have to perform the splay operation on 7. When we perform the splay operation on 7, we're going to take 7 to the position of 9, and this operation will be ZigZag operation. So when we perform that, we have these three restructured to look like this. Now let's use the second method to perform the deletion. The second method here is to perform splay first before performing deletion. So the splay is we're going to move 6 to the root node, and the first move we're going to have is using the ZigZag rotations. And the ZigZag rotation, we first take 6 to this location, and the next operation, which is going to be zig, we take 6 to the root node. So the 6 is at the root node, but what we want to do is to delete 6. So we now have to delete 6 and restructure this tree to look this way. So finally, what we're going to have is the same or similar structure from what we had in the previous operation. So this is the final result. So any of them could serve the purpose of deleting 6 from the tree. So that's the reason we say deletion is in two different ways, and it doesn't matter or necessarily matter. The outcome might finally look the same, or they might not look the same. Finally, we have to insert node item 11. So for us to insert node item 11, we perform the binary search operation of inserting an element into a tree. So which we know that we first of all compare the element we want to insert with the root node. And if it is greater than the element at the root node, we have to move right. Then we have to compare it again. If it is less than, then we have to move left. So this is the location of the item 11 that we have inserted. So, but when performing splay, we have to move this item 11 to the root node. So what kind of operation are we going to perform at this point? Is it going to be ZigZag operation or ZigZag operation? So in this case, we're going to move to the right and move to the left. So we're going to perform the ZigZag operation. So when we perform ZigZag operation, we have the structure look this way, and that will be the end of the insertion operation. So finally, we have explained the splay tree. We have also tried to give the differences between an AVL tree and a splay tree. We perform some operations such as deleting, inserting, and searching for an item using the splay operation. So at this point, we're going to end the lecture here. But before we do that, there's a kind reminder that you need to attempt the questions on this workshop 7, and you can find them in the module. Thank you very much. And do send any questions about these slides to me, or ask Darlene some questions if you need. Ask, send your questions to Darlene. And at the same time, if you need any support, please kindly let us know. Thank you very much, and bye.